So what is metastable state? So you have a stable state here, right? And this is a metastable state. For example, this is not a stable state, it's a metastable state, right? This will be your stable state, right? So if you give a small, right, energy barrier, which this is the energy barrier, it's a metastable state. They can stay in the metastable state as long as there is no external perturbation, external force which can change the state actually, right? So if you give an energy of this, then it can go to the stable state. So the whole the phase change property is based on this, right? If I have energy, if I supply a sufficient energy to cross this barrier, then it's going to go to a stable state. And bringing back to from the stable state to the metastable state, you have to spend a lot of the energy but it's possible actually. Okay, right? From this state to this state, one can even bring back, and that's the way from this state to this state, they write the information from this state to this state, like from stable state to metastable state, the information can be erased. So one can do a write operation and erase operation by having the sufficient energy barrier to have the energy to cross this barrier actually, right? Oh, fine. So this is a crystalline. I mean, it's SiO2 in a crystalline state, in the amorphous state. For example, crystalline state, you have each silicon need 4 neighbors actually, right? 4 oxygen. So each oxygen will need 2 neighbors, right? To silicon. So it's a SiO2. You can see these SiO2. You have tetragonal structure because it's a 2-dimensional structure. You will not be able to see the 4th one. So here we have shown actually this is silicon. You have 4 neighbors actually, right? So this pattern is repeated in a periodic way everywhere. The same SiO2 in a amorphous phase. You can say same basic unit, but the way they connect to the next unit, there is an error in the connectivity. Like there is a bond angle error or a bond length error that creates disorder, and the disorder propagates to the whole structure, and you have a very, very disordered structure. So how do you achieve this? People must have read about crystalline materials very well, because it's from 9th standard, 8th standard onwards. You have crystalline, so we study about the crystalline materials, but not much on the non-crystalline materials, because it's not a well structured. I mean, I don't think the regular syllabus is on amorphous materials. So to achieve this disorder, there are methods to like achieve this disorder that we will see how we do that actually. Before that, like we have, I mean, various kinds of glasses. Like we have glasses and inorganic glasses, organic glasses, and even metals can be made into glasses. And then in the inorganic, you have oxides, non-oxides, and halides. And so we concentrate on non-oxide glasses. You have 2 types of non-oxide glasses. One is tetrahedral, that is group 4 based silicon and germanium, well known semiconductors, silicon and germanium. So they can be formed into amorphous state. And from then they have a chalcogenate glasses. It's based on group 6, as we said, and they are called something called lone pair semiconductors. So that we'll see. I mean, why they are called lone pair semiconductors. That brings a lot of interesting properties to the electrical. Most of the electrical properties are controlled by these lone pair in these glasses actually, right? So before that, I just want to emphasize, right? Glass is a very, very vast field actually. Most of the glass studies are all centered around oxide glasses, because oxide has the huge market. About 95% of the market is oxide glasses. Only 5% is these kind of special glasses like what we are talking about. So most of the research and studies industries are all based on the oxide glasses, SiO2, right? The window glasses we see, right? We see the outside world through the window, because it is transparent to visible light. There are glasses which we are talking about, they are transparent to infrared light, right? The night vision, many applications are there with these glasses. You'll not be able to see the infrared like IR applications in this talk, because time is limited. We'll see some other time. But here we will see only the phase change properties. Before that, I just want to emphasize that glass is a vast field, and you have any scientific discovery you name, glasses must have been involved in this. Glass made the scientific discoveries very, very easy. For example, X-ray was discovered very. It has helped actually. Glass has helped actually to discover the X-rays, because so he was the Röntgen was studying the gas discharge properties of gas. He evacuated a glass tube, and put small amount of gases, and then he was giving high voltage and studying the discharge. So in that process, he saw some fluorescent screen far away was glowing, and he found, he thought, okay, something is pass through a large distance, and obstacles also it can pass through. That's called, he named it the X-rays actually. So what I'm trying to say is, many of the discoveries are enabled or are made possible by the existence of glasses. Actually, they are transparent glasses. So, for example, we have listed some of the things like, Thomson discovery of electrons, Faraday's electrical. So the Faraday's work, which connects the electricity and magnetism, that was possible with the Crookes tube and electron. Many of these like apparatus made by the glasses actually, right? So we'll move on to the glass formation. How do we form the glasses? So, if you are doing a glass science, glass research, one of the first thing you encounter is this volume versus temperature. It can be volume, entropy, enthalpy. So how do we? This simplifies the glass formation. So this slide itself can be now for half an hour or 40 minutes or 1 hour. You can talk actually with this one single slide. So there's a wealth of information. So, but we see how simply, how the glasses are formed. For example, if you want to form some glasses, let's say group 4, 6, germanium and selenium glasses we want to make. What do? You just take them and evacuate with a vacuum system and seal them under vacuum, like a quartz tube. You put your material and evacuate and seal under vacuum, and then take it to the high temperature, like so the melt state, right? You homogenize the melt, and now you have a stable liquid there. And two ways one can cool this, like remove the temperature, cool to the solid actually, right? So the stable liquid I have. So if I give a lot of time, if I slowly cool the melt, I'm giving a lot of time for the atoms to come around, right? So when you cool the temperature, when you cool the liquid, the other property of the liquid is viscosity, right? Viscosity inversely proportional to temperature, right? So resistance to flow, viscosity is resistance to flow. So when you decrease the temperature, viscosity will increase. So the atoms movements are restricted. In a liquid, a high energy, you have a lot of energy for the atoms, so they will be randomly moving here and there. And so when you decrease the temperature, you are reducing the energy, so they are also viscosity increases, and the atoms come closer and closer. They make a bond actually, right? Once they make bond, they lose their energy, and once all the bonds are formed, they lose energy, and there is a sudden change in volume. They become a solid actually, right? The first order transition, you can see. So they go to order because you are given a lot of time, so they sit in the regular position and take a periodic arrangement of atoms. So they go to a crystalline state, which is low energy state, so equilibrium state, right? So what we want, we don't want this to happen. So what we do, we suddenly remove the temperature. And so how do we do that? So you take the melt and put it in ice water or liquid nitrogen. So the delta T, the temperature difference, like between this and this is very high, like about 900 degrees centigrade, and you do it in a milliseconds or in a few seconds actually. So the cooling rate is very, very high. So as a result, what happens? I have a high temperature liquid. I am just taking the temperature very fast. As a result, the atoms don't have much time to find its neighbor, and they get confused actually. So as a result, liquid remain as a liquid actually. So it's very strange actually. So even before, below this melting temperature or freezing temperature, the liquid remains as a liquid actually. It's still not well understood why the liquid has to remain as a liquid even before its freezing temperature. It's an open question, still people are trying to understand, but this is what happens actually, right? So the liquid remains as a liquid, but the other way, the viscosity increases when you decrease the temperature. So the liquid becomes high viscous liquid actually, right? So they enter into a supercooled liquid, and at one point of time, the viscosity of the liquid reaches the viscosity of the solids actually, right? So about 10 raised to 12 or 13 pies, which is the viscosity of solids. So my liquid is now a solid actually for all mechanical purposes. Mechanically my liquid is a solid, but structurally I have arrested one of the disordered state of the liquid and brought to the solid. So structurally they are liquid, but mechanically they are solid actually. So we have a liquid and a solid at the same time. That's what the glass is actually. The transformation from high viscous liquid to a solid happens at a temperature called glass transition temperature, right? So this is very important property for the glass actually. So this, when for example, if within this supercooled state, if you cool it very fast and little slowly, you can change the volume of the liquid also. So this has a lot of applications, practical applications. For example, your window glasses, your windshield in the car, many glasses, many for applications. This property, right, has been explored for or exploited for strengthening the glasses. So we will not have much time for that to explain, but I'm saying this has been explained. This has been explored for strengthening the glasses. A lot of industries, a lot of work is how to strengthen the glasses has been done actually. Right. So this control of this liquid state to the solid can be controlled by two time scales. One is the internal time scale, another one is the external time scale. Internal time scale is how do you, this is a bonding, right? We can make a strong bond or a weak bond, and number of different kind of bonds one can make between different elements. You can put a lot of elements, so the different kind of atoms and different kind of bonds will form, and they get confused, and you can make it a glassy state. Yes, they should. When they get confused to whom it should bond or not, by the time you can quench them back to the glassy state, right? So external time scale, as I said, cooling rate, right? So how fast you can cool. I can use different cooling mediums and I can cool it to the glassy state, right? So in principle, that what it says is anything can be formed into glass provided if I have a cooling rate, right? For example, water, right? I just give you an example of water. Water is very difficult to take it to the glassy state, right? Because, for example, you need required cooling rate about 10 raised to 6 Kelvin per minute, actually, right? That is very huge, actually. That means what? 300 to 150 Kelvin, I need to cool it in 9 milliseconds. So that fast you have to, because the reason is that the water molecules, H2O molecules are all individual molecules. So they can take any configuration, they can sit in any place. So very difficult to crystallize actually. So you need to have a high cooling rate. Whereas SiO2, there is a strong glass former. You can see that 10 raised to minus 10 Kelvin per minute you can cool. That means what? 2000 degrees centigrade to 1000 degrees centigrade in 20 million years. You just do whatever you do, it will go to the glass system. That's what SiO2, window glasses, for many application bottles, many things are all easily, or you can see many ornaments and are made of glasses, SiO2 based glasses actually, right? Okay. So I said as it's a liquid actually. What is the proof that a liquid is now in a solid actually, right? For example, if I have a solid glass, if I heat it, so at the glass transition temperature, what happens the other way, right? I have a solid, mechanically it's a solid. Now I heat, it goes to the glass transition temperature where when I come from the other side, like liquid side, it goes to a solid. I mean, it loses its rigidity, right? Now I am going from the solid, so it should lose the rigidity. It gained the rigidity from the other side. Now at this point, it should lose the rigidity. That means it should soften at the glass transition temperature. It's not melting temperature. It's 2/3 of the melting temperature. It's very low from the melting point, but it loses its structure. So in a solid, you have only the vibrational motion, right? So it leads the specific heat. What is specific heat? To increase 1 degree, how much energy you need to increase the temperature of an object by 1 degree, right? That's a simple, simple definition. So whereas when it enters the liquid state, it has rotational motion and there's a translation motion. So you need a lot of energy to make them to happen actually. So yes, jump in specific heat will happen. So that is one of the evidence for these are all liquids actually, right? The glasses are liquids because of the high viscosity. They are all solids actually, right? So this jump is also one of these how much it jumps. There also, the CP, right? Specific heat from solid to liquid. This jump also has wealth of information like about our liquid actually, whether it's a strong liquid, whether it's a fragile liquid, many of the things one can study, and based on that information one can design the glass for specific applications. So this is one of the important property for the glasses to choose for specific applications, right? So when we come to sarcogenic glasses, because the talk is basically on sarcogenic glasses, right? So we have sulfur, selenium. This is group 6 element, sulfur, selenium, tellurium. And as I said, we have to take it to the melt state and quench it fast. Will form a glasses actually, right? So they are all mostly semiconductors and covalent bonding. So one of the other aspect of these glasses is that they cannot be doped. They are semiconductors, but you cannot dope them. So why you cannot dope them? Because the defects which present due to the disorder arrest the Fermi level at the center of the gap. You cannot move the Fermi level. Only you can change the width of the conduction and valence band. So you put more of more carriers, charge carriers. So one can change the width by alloying actually. So but people interchangeably, they use doping, alloying, many other things. So this is like loosely in the chalcogenate community, they use doping as well as alloying casually. So it doesn't mean that you can dope them actually. So you can just add the atom elements to the chalcogens. So because this is based on the 8 minus n rule. What is 8? This is octet. No? If you see the outer shell electrons, the 8 electrons is if it has a stable structure, right? So that's what the group 8 like krypton, all the inert gases, argon, krypton. So they are stable and they cannot react with any other things. That's what many of the experiments, like if you don't want the impurities or other gases to interact with your system when you're doing some experiments, most of the things are all done with these inert gases actually, under the inert atmosphere. That's because of they have a stable outer electron shell. Right? So for example, so these gases cannot be doped because they obey 8 minus rule. So if, for example, group 6 element, if group 6 like sulfur, selenium, tellurium, they have 6 valence electrons, and 8 minus n what? 8 minus 6, you have 2. So the valence will always be 2. They have coordination between, for example, sulfur will have another sulfur or other atom like two neighbors actually. So that's the way. So if you put germanium will always have 4. Germanium is 8 minus 4, so group 4 elements, 4 valence electrons, it will always be in 4. Arsenic or antimony, if you put, they are group 5 elements, 8 minus 5, 3. So whatever you do, they will adjust their valence to obey this 8 minus n rule, right? So I said like they are called lone pair electrons also. Like lone pair electrons means, for example, if you take germanium, they have 32 electrons. They are group 4 elements, like tetrahedral semiconductors, and you have 4 electrons, outer shell electrons. So 2 occupy the S state and 2 occupy the 4p. So they go to sp3 hybridization and we have bonding and anti-bonding states. This is the optical gap actually, right? For example, if you take selenium, which is group 6, so you have 34 electrons, 25 occupy the low energy orbitals, and 6 electrons occupy like 2 4s electrons, and the paired and the 2 unpaired. So these two of them form a bonding band and 2 of them form a lone pair. So the lone pair, which is little higher energy, and they form the valence band, whereas the bonding band, right, so forms a low energy state. So they These valence band, sorry, the lone pair will not participate in bonding actually. They are available as lone pairs, they will not participate in bonding, and in some conditions they participate in bonding and alters the electrical properties to a larger extent. So most of the electrical properties are controlled by these lone pair electrons actually. That's what they are called, lone pair electrons, lone pair semiconductors actually, right? So I'll not get into this. And one of the interesting observation, great scientists, I mean, he was the Professor Jigmar was talking about great scientists. One of the great scientists in glass science is J.C. Phillips, actually, right? So he was looking at some of the properties of chalcogenic glasses, and he found that in many of the systems, he found some anomaly in some of the composition, one of the compositions, right? For example, here, if you see here, As to Ac3, this specific heat is very, very sharp, right? You can see very sharp. Others are not sharp, right? And many other things, like many other properties also, he looked at that and he observed, oh, there is something is very special about these kind of compositions. Like, so he measured the width and it was very, very minimal, about something called arsenic 40% actually. So then they also studied the glass forming ability in group 4-6 elements like germanium, selenium. You can see this about 20% of germanium, the glass formation is very, very easy. That 20% is belong to some particular coordination number. So if you take a germanium, the nearest neighbors, and if you take arsenic, how many nearest neighbors? So that, I mean, average neighbors, it turns out to be something called 2.4, right? For example, if you take a network glass, you have bonding between two atoms. So one can, the constraint about the bonding is like you can stretch, right? It can stretch. So the bond is shared between two atoms. So you have R/2 stretching constraints. And if you take a centrally connected atom with the two atoms, you have a bond angle. So you can just move like this, and it has a constraint. Centrally connected atom has a one constraint, and you have two, right? Two other atoms connected here. So you have one constraint for a centrally connected atom, and then you have the rest of the, so R atoms are there in the system. Rest of the R-2, because you have considered two, R-2 atoms will have constraints, and because of these two atoms are already considered, so you have two constraints here. So if you balance with the number of degrees of freedom available for the atoms to move, so number of degrees of freedom is 3, if you equate, it will be about 2.4. So average coordination number, if you have 2.4, you have a special property, anomalies in the properties, right? For example, glass formation is very easy and they are stable, they don't undergo aging, and they don't relax easily because I said this was structurally liquids. So liquids will have higher energy. Atoms are trying, because they are in the higher energy, so higher energy state will always try to go to the low energy state. So they relax. How they relax, how fast they relax, that decides their application in many of the devices actually, right? So they should have something called, they should not age with the time. So if they age with time, they go to different states actually, right? So if they go different states, then their electrical property is going to change, optical band gap is going to change, and their rigidity is going to change. So that will affect the properties. So you should know what kind of what is the coordination number of the system what you are studying, and that will give you some idea whether it is okay to go for the devices or something, right? So this is what, like, so you can observe many of the interesting properties at 2.4, like maximum at glass transition temperature and many other things, right? So, right. So in the laboratory, I said, like, you take you take the material in a quartz tube, prepare them, like rock weight and seal them, and then put them in a rocking furnace, which can rock, right? The melt can be homogenized. Then you put it in ice water and you get a bulk glass, right? And the basic characterization techniques are X-ray diffraction, differential scanning. Because X-rays, what I mean, like they work on the principle of Bragg's law, n lambda equal to sine theta, right? So you need to have a constructive interference for so we'll not go into this because you must be knowing all these things because we have not much time. So, for example, if they don't obey this law, you will have only the background, right? So that shows the glasses are they formed a amorphous structure actually, right? So there's a difference also between, I just forgot to mention the difference between amorphous and glasses. Amorphous, any disorder in the atomic arrangement can be called as amorphous, right? The glasses are subset of amorphous state, amorphous material, because the amorphous materials when you heat need not exhibit a glass transition temperature, whereas glasses will exhibit a glass transition temperature. Then you can say glass actually, right? So the first thing when you prepare a material, you need to check whether it's amorphous, right? If they are amorphous, then you will not have any Brock peaks. Whereas if it is glass, then you will have a different kind, I mean, like sharp peaks, like which obey n lambda equal to 2d sine theta Brock's law, where constructive interference happens and you will have Brock peaks actually, right? So the next step is you do a differential scanning calorimetry, like calorimetric studies, right? Calorimetry is what? Any phase change, what is the energy change in the process? So when you heat, so we all are, because we said like the temperature from high temperature to low temperature you quench. So due to that, there are stress in the network actually, right? Because you don't have, there are a lot of deviation in the bond angle, bond length, all these things. So they will try to relax by giving these, taking this energy supplied, and at one point of time, the glass transition temperature they will rearrange and go to a glass, I mean the softened state. So they take the energy from the supplied, I mean, whatever you heat energy you supply, this is an endothermic reaction because they're taking the energy, and if you keep heating, then it goes to the crystalline state. This is what will be exploiting in these phase change materials. So you give energy, right? You can change the state from amorphous to the crystalline state. So it goes to crystalline state, it gives away its excess energy and go to equilibrium state. Further heat, the bonds will break, then you go to the melt state, right? That's what we see from that figure previously, right? Okay, so I said like at this point it softens, actually the glass transition temperature softens. Many of the lenses they make actually, right? You take the material to the glass transition temperature where it softens, and then you make a mold. For example, you want a sphere, you want a lens shape, you make a mold of that and put some pressure, you can change the shape. This is what the companies will make lenses actually. You don't have to go to the melt state to make a shape, or you don't have to grind them. So it's a easy process. Having said easy, it's not easy actually, because you have to design, take into many of the things into account to make this mold actually. You need to know the thermal expansion, how the refractive index, many other things you need to know how, I mean, these molds can be made. But the thing is, you don't have to machine them. Like for example, germanium is used in infrared transmission. So germanium is one of the well-known materials, but germanium is a crystalline material. So you need to grind them, very expensive also. Grind them, polish them, and take it to a lens shape actually. So in this process, you lose a lot of material, a lot of labor, and also it's poisonous actually, right? So any chemical is poisonous. So to avoid that huge laborious process, you can make this mold and you can get it as shape. This is one of the advantages of glasses actually, right? At the glass transition temperature, they soften. That is exploited for these applications actually, right? So coming to this non-volatile memory. So what is a non-volatile memory actually? That's what the main theme of this talk. So because I just prepare you for what is the glasses, how you can change the glasses from like amorphous state to the glassy state. I mean, sorry, crystalline state. So that's what I just made this. I hope you understand how there are glasses, they are amorphous state, they are high energy state. You can give some energy to cross the barrier. They can go to the equilibrium state, that is crystalline state. And these two states have huge property difference. So there are many glasses what we listed in some of the previous slides. These glasses will not have that kind of property difference. All the glasses will go to the crystalline state, but the property difference between these two states are not appreciable in many of the other oxide glasses or metallic glasses. But chalcogenate glasses has a huge property difference, like 1000 ohms. If you take refractive index, it's about 30%. If you take reflectivity, it's about 30 to 40% difference. So these are the properties people exploit for storing information actually, right? For example, your CDs or DVDs are all of the chalcogenic glasses. CDs you must have seen actually, right? If you buy a new CD, you can see it's very shiny actually. It's a crystalline state, right? Very shiny. When you write, after writing, you see it's the portion is very dull because it has transformed to the amorphous state, right? So its reflectivity is very low. So when you send a read pulse laser and you see like it sees the reflectivity difference between these two states and gives the corresponding information. So CDs or DVDs are of chalcogenic glasses, which is now obsolete because now we have the flash drives, pen drives, which is also has some limitation. So how to overcome this limitation? That's what these phase change materials people are looking for. Okay, so a lot of information. The thing is that you have information pouring actually, right? You have satellites, many satellites for specific purposes like seeing the depletion of forest and astronomy and data and health data, many things. So you have a lot of data every day is pouring. So you need to have systems or memory materials which can store the information, like the storage density should be very high, and also scalability, right? Now we are reaching scalability limits. So these kind of things, can be overcome by using the phase change memory materials. That's what many people, many research groups are working on this. In name any semiconductor industry, they are all into this phase change memory material because they have potential to overcome all these data storage density and scalability and multi-storage levels. Like for example, in a single cell, you can store many memory states actually, right? So because usually you have memory cell, you have one byte you store, one state. Whereas here you can store many bits actually. So that's what it gives a lot of scope for memory storage actually, right? So what is the phase change? As we said, you have amorphous state, give some optical pulse. Those are CDs and DVDs are all that kind. Now we are looking for electrical memory, right? You give electrical pulse, you can change the state from amorphous to the crystalline state, right? So that's what we are doing actually, right? So why we have to worry about that? Because this is random access. We have in computers random access memory, right? So when you switch on the computer, it takes long time because all the information is hard disk, which is a sequential memory, and so it takes information to your random access memory, right? RAM, right, which is closely placed with the CPU, right? So because the process can take faster, so it takes long time to load the information there, and when you do some operations, so for example, you are typing something, Word document or something, it stores in the random access memory, right? So random access memory is what is that? It's based on the capacitance based memory. So it's a charge, right? The charge state, right? Whether it's a full, the capacitor is full, it's a 1. If it is empty or if it is not charged, it is actually 0, right? So the problem with this is that the charge tend to leak actually, right? So every millisecond you have to refresh to hold the information. So that's what, when the power goes, you lose the information, right? For example, you're typing and you are saving, then it goes and write in the hard disk, right? Hard disk is sequential memory, so it cannot write randomly there, right? So one has to give way for the memory, for the information to store. So it takes long time. That's what the sequential memory drawback of this sequential memory. Whereas random access memory, it writes wherever the place is there. So that is very fast. But the problem with this is the charge tend to leak, right? So you have to compensate by every millisecond. So a lot of power is needed actually. And also once the power goes, you lose the information. Whereas that's what it's called volatile memory, right? You need to have some power to hold the information. Whereas what the kind of memory is what we are talking is about called non-volatile memory. As I said, it's a structural change from amorphous to crystalline. It's huge energy change, right? So you cannot go back to the amorphous state unless you forcibly do that. So once you write, whether you have power or not, it is stored there, right? So that's called non-volatile memory. So once you write, you don't need any power to hold them actually. That's what it says actually, right? That's what we explained, and this is what like for example, I said the group 4 element, group 4 semiconductor. If you see the reflectivity, there is no change at all. Whereas in the chalcogenide, you see about 30%, 30 to 40% difference in the reflectivity. That's what is called phase change memory, right? If you see the resistance, it's a huge change. About 30, about 100, 1000 ohms or 10,000 ohms difference between these two states. So they are, so I'll just close it, right? So how do we do this actually? So you have an amorphous state. I give an electrical pulse, right? Electrical pulse of little longer time. So it heats the material and take it to the crystalline state. So the heating is due to the Joule heating, right? So every material has its own resistance, right? Internal resistance, and so due to this resistance, the current flow will be obstructed. Once the obstruction happens, the heat will be generated, right? So the heat is enough to crystallize the material from amorphous state to crystalline state. And if you want to bring back to the amorphous state, you give a high current pulse, right? For a shorter duration, give a high current pulse. So locally melts the material and quenches back to the amorphous state. So you can write, you can erase the information, right? So if send a read pulse, you can read the information. So that's what the material. So I just want to, this discovery is not very easy. It's a painful discovery, and this will be very inspiring. I just want to share like maybe 5 minutes about this person. His name is Wojcinski. He's like school dropout. He's a school dropout, but to his name about 600 patents are there, right? He name anything, he is there. Any field you take, hydrogen storage, battery materials, anything you say, he is there actually, right? So he is a school dropout because he's very poor family. His father is a steel scrap merchant actually. It means what? You go to the lathe, you're machining, there's a steel scraps are there. So he goes and collects and then sell for his daily life, right? So he goes with his father to help him. And when he goes, he sees the industry, like lathe machines, huge lathe machines, and he's inspired by these machines actually, right? He wanted to become a like lathe man. Then he wanted to make big lathes. That's what his aim. So, and also from Ohio, where US, where rubber industries are there. So he knows about the rubbers. Rubbers are soft materials and also formed from the polymers, right? Polymers are chain-like structures, very flexible. So he knows about the rubber and polymers and the flexible chain-like structures. So this is all experience. His observations and experience made him to like huge success in industry actually, right? So then he got a job in lathe, this thing, and he was lathing all these things he was doing. And one time that's the scrap, right, got into the it obstructed the power. Right? A lot of dust accumulated, and he was cleaning, and it was boring actually. So one time he was giving high voltage, right? Then he started working. So that's where he gained the knowledge like the switches, right? So this itself can act as a switch. So instead of just cleaning, so one can increase the voltage, one can increase the decrease the voltage, so one can use it as a switch itself. So he gained the knowledge for switch. Then he made automatic lathe, big lathe, automated. So his own discovery. That's what listed. Shown there. And also this is a lathe machine, automated lathe machine. He made actually, right? And also then he got a job in some biology department, biology industry, biotechnology industry actually, right? So where he has to study the DNA. DNA is a chain-like structure, right? It's a hexa chain kind of structure where the information is stored there. So he studied that, and then he thought, okay, now we need to make something to store the information and transfer the information. That's what the knowledge he gained there, because DNA store the information and they pass on to the next cells or generation also, right? So he proposed that the information stored from, transfer from one place to other place in the body, right, through nerves, right? So it's called neurons. They conduct the information from one place to other place. And he said it's not that momentary like they transfer. So the information comes and stores, and then at one point of time when enough information is accumulated, it transferred to the, this is called snaps and then synaptic weight. That's what they say in the scientific term. The weight is, the synaptic weight should be high enough or should cross the threshold level, then it goes to the next neuron. That's what. So he was talking in the 60s about the neuromorphic memory, which is hard now, right? People are now trying to mimic the brain and how the information is stored and how the information transfers. So they want to mimic the brain now. So this is what he was talking in the 60s, late 60s actually, right? He not only gave this proposal, but also showed practically that he took a electrode system, two electrode system, like three electrode system. So he filled with the salt solution like KBOH or NaOH solution. Yes, body fluid is a salt solution, and these electrodes are tantalum, which is like oxidized. The oxide state is the amorphous state, right? So when he controlled the current between these two electrodes, right? At one point of time, at particular voltage, the oxide layer is removed and it started conducting, right? So that's what he said. So you have to have enough information so that it can pass on to the next cell, right? So he gained the knowledge of controlling the threshold level, threshold switch kind of thing. So all these information, all these he gained. So then he wanted to start his own company to make these memory materials, neuromorphic memory materials, and he was not having enough money. So he has this industry patent, like the lathe patent. He sold and started a company called Energy Conversion Devices, and where he wanted to study the memory properties. So he knows it should be a soft material, like chain-like structure, which can be flexible, and you can be able to tune the the rigidity of these chains, so that one can tune the properties actually, right? So he selected sulfurs, the group 6 element. That's what the chalcogenates came actually into picture. So because these are all twofold coordination, so it's a chain-like structure. So they're flexible. So he chose these materials, and to control the rigidity, he chose group 4 elements and group 5 elements. Group 4 are four-fold coordinations. If you put germanium, they can cross-link the chain, right? So they can increase the rigidity. If you put group 3 element, they can branch these cells, right? We can connect to chains actually. So he made a composition called STAG, like silicon, tellurium, arsenic, and germanium. This composition, and asked one of the subordinate to make the thing. So they were not having any deposition system, infilling deposition system. So they powdered the glassy STAG thing and put between two electrodes and trying to pass some current, and it was not working that great because the connectivity between the particles are not that great. So they were not observing anything. Instead, the worker got a arsenic poison. The arsenic poison leak. So he got vomiting and then fainted, all these things. So he was worried, and then he has been admitted in the hospital, and he was thinking in the other way that, so if he is arsenic poison attack, then he must be inhaling something. That means some vapors are coming from the material. So that vapors must be deposited on the probe, right? You put electrode, two probes you put, then he thought this must be coated on these two electrodes, two probes actually. So he took this probe and to use them as the material, what do you call the phase change material itself, and pass current between them. Then he observed this thing. So you can see this is like the voltage IV characteristics. The voltage increases at particular voltage, it switches to the high conducting state. So this oscilloscope is also designed by him. So very interesting person. So the discovery of this reversible switching. That's what is that means? It goes and stays in the high conducting state. Once you remove the applied current, supplied current, it comes back to the original state. That means what? It's not non-volatile, but it is a memory state. But once you remove it, comes back. So he wanted to have a memory thing. So he asked one of the subordinate to change the composition and study the properties. So after some time, the worker came dejected and say, "Sir, this material is not useful. What happened? He asked. No, I just throw it about. It's my waste of time. All this thing he was talking. Then he said, "What? You tell me what happened." He said, "Sir, it switched actually. Go to the high conducting state. It is not coming back. It stays there." Then he said, "Okay, you have observed a great thing. It's a memory material. It stores actually, right? Once you write, it stays there. So you don't need anything to store hold the information. So that's what non-volatile memory came into picture actually. So they, I mean, like made into actually a market after that. And so, I mean, till 1887, there are a lot of companies try to exploit this property, but not successful because the crystallization time, right? It's about milliseconds. Nobody wants to wait till the right time or read time to that thing. So then 87, there was a material which came into picture, Germany multimeter, which are CDs and electrical memory. Now they are available in the market. That's what the things came. So okay, so I'll just maybe stop because there is no time. I don't want to extend the thing. So these are all about germanium arsenic, what we have done in our lab. Uh, so one of the things I just want to show is what we have done. We have prepared the amorphous germanium multimeter, which is the actual memory material which is stored in, which is available in CDs or electrical memory also available now in the market. Micron and IBM have developed actually. So okay, so these are all like the germanium multimeter has three structures. One is the again. Then the amorphous state, we have a cubic NaCl structure, then hexagonal structure, right? The cubic structure has some vacancies which has give the flexibility between amorphous and crystalline states, and due to that, the transform from amorphous to the crystalline state is very easy actually, right? At little higher temperature, it goes to the hexagonal structure. The NaCl structure is the metastable state, so it won't be. It is not a stable state. And what we have done, we have put arsenic in place of antimony, like some part of the things we replaced, and we see the crystallization speed is increased, and the power required to switch them is very less actually, right? So will not be much time. We can see the IV characteristics. This is the germanium multimeter. You can see the arsenic. When you put it, it switches at the lower current actually. So the power required to switch them is high, very less. So it can be, and also the data retention, how long. So this is one of the other important properties is how long you can store, how many times you can write and read, endurance. Many of the properties are important. So it is showing high, very promising thing. That's what. So I'll close it. I can take 2 minutes. 2 minutes?
Yes.
Yeah. Okay. So the other important thing is now, like I just want to mention this. So you are seeing me, or I am seeing you by how the reflection of light, right? Light falls on you, and it reflects to me, and I am seeing. It's a pleasant, very pleasant thing to see these posters or whatever, like by reflection of light. But how do you see in your cell phone or movie theaters or your screens? It's not by reflection. It throws light at you, right? It's not by reflection. It's a very unpleasant thing where you get eye pain or these things. When you go to a movie theater, what happens? You have to close the theaters and you have to see in the dark actually, right? This is all because it throws light at you, not reflection. So people are now trying to make dynamic displays actually, right? Because a photo is a static display. It gives the reflection, whereas the dynamic displays, the movies and other things are all by throwing light at you, right? So now they are trying to make dynamic displays by reflective mode, which can be, you can see it any place, anywhere. You don't have to worry about the sunlight or anything. So that's what people are trying now. That is the inspiration from these nature actually, right? For example, if you take a butterfly or peacock, how they get different colors? By interference, right? They have thin films of varying refractive index. So the light interferes with the different kind. When it faces the other, different refractive index material, the light speed changes. So they interfere. They consider interference happens. So this is interference, right? So you have two waves, and they have in phase. You get a enlarged one, right? If they are out of phase, they cancel out. So this is the principle they use for dynamic displays now, right? For example, this is a refractive index I said. This is, we know, very famous figure, right? This is a phase change material. What we had talked about phase change materials, I said refractive index can be 30% difference actually, right? So you pass the light, and so you can change the refractive index of the thing so that you can control the light, so you can use it for phase, I mean, like dynamic phase change memory displays. That's what a lot of work is going on. So maybe in few years you'll have the dynamic displays which you can see at any place kind of thing, right? This is another application of these things. For example, you have sunlight which has majority of the portion is IR light, which we cannot see actually. So by coating this phase change material, I just pass some current, I can change the state amorphous to crystalline, but it will not, the light will not affect actually, because you will not, anyway you are not going to see the IR light, but IR light are heat rays, right? You can cut the heat rays by changing the refractive index, so the room will be cool, I mean, will be cool. So you can, there are many applications of these phase change materials. One of them is this, right? So in summary, right, you have a material, right? So you have a amorphous material, you can set a set pulse, you can crystallize, and then write the information, you can melt it, punch it, you can have the array, I mean, you can erase the information, you have, these are all non-volatile as I said. So this is the thing, right? So these are all available in the market actually. A lot of work is been done actually. So they are available in the market now, electrical memories, but still people are trying to increase the endurance, repeatability, and storage, temperature, many of the things, right? So this is my research group, and I just want to mention, because of him, this research is going on. This is my supervisor, this is my postdoctoral supervisor, one of the other great inspiration to all of us, Varshnaya, she mentioned actually. I just, 1 minute, I just take it. This is a great person actually, right? So he has a Saxon industry. You can go Google and Saxon Industries actually, right? What he did actually, he is from Agra actually, right? His family is a glass business family earlier. He moved to US. He's a professor in Alfred University. He's now retired. What he did, the glasses, which are all very fragile actually, right? So when you quench, you get a lot of stress, so it's fragile. Small force you put, it fragile. So in the US, if you go to the countryside, like village side, you have to pass through forests, right? When you travel in the highways, so there are forest bees, forest things. So if they bite, it's a fatal actually, right? Within I think 30 or 60 seconds, you have to inject medicine actually. So the people who travel the countryside, they have something called epic pen filled with the medicine actually. So once they bite, you have to put it in your thigh in a particular angle actually, right? So people get tensed and they break. This is a glass syringe, it breaks actually, right? So he made a way to strengthen these glasses actually, right? So something ion exchange. So sodium, these are soda lime silicate glasses. Sodium is a smaller atom. Potassium in the group is a bigger atom, right? So in the materials, the compressive stress is higher. I mean, has high strength. Tensile stress is low strength. About 10 times is higher than, I mean, the tensile. I mean, it is the kind of compressive stress is high actually. Strength. So if you have a material which compressive stress, its strength will be more actually. So one can. So he by ion exchange, by replacing sodium with potassium, he strengthened these glasses, and many thousands, millions and millions of lives he saved. So I just worked with him as a postdoc. It's a very fortunate thing, very dynamic, very lovely person. So he saved millions of people by his research, glass strengthening. Okay. So thank you for listening.